So now it's recording, so I'll also post this online for you to view. Feel free to ask me questions as I go along. So as I said, the first question we'll look at is here. This is, I believe this is question 2 on the practice exam. So looking at this is the circuit drawn out to begin with. Starting, we're given 2 or 3 things. You'll usually be given a couple parameters that are just going to continue on throughout the whole problem. In our case, we're given beta, our early voltage, and our Kn, our transconductance parameter. So our beta is set to 100. None of these values you're going to need to solve for. These are given to you. Early voltage was set to beta, sorry, just 100 dimensionless. Early voltage is 100 volts. And then your transconductance parameter Kn is set to 10 milliamps per volt squared. They're given to you, don't need to solve for. What we're asked to find by the problem is we want gain, and then we want our in, or what I'll just do input, output, IO impedances. So I would say I would just looking at this upon first inspection. Something I would immediately notice is the 1 milliamp current. We have current source down here. We have our signal. We have where R in's coming from. We have our R out here. That'll help when we're beginning to redraw the circuit. We have our resistors there. The main thing, though, that's going to help us from first inspection is this 1 milliamp, because we're looking at common base, because we have our emitter, collector, and then base. And we'll see that our base there, which is here, where the 20 kilo ohm is connected to ground. And we're not going to have a current there because of that. So we'll have IB, base current, is 0 amps, and we know what our current at the emitter is. IE is 0, sorry, not 0, is 1 milliamp as given by that source. Well, because of that base being at 0, we know what the collector current is, because the collector current is equal to the emitter current minus the base current. Where you'll see this equation in your sheet, but it's going to look like this. It's going to be I at the emitter, the current is equal to the collector plus the base, or base plus collector. You just rewrite this. If you know 2 currents, if you know EB, if you know CE, CB, any of them, any 2 of the 3, you can always find the third. So we do know 2. So now we know the third, that IC is the same thing. It's 1 milliamp. That's our first thing we can solve for. That'll help us out. Continuing on from there, you'll see on your equation sheet, you're given R pi, R out, little RO, not this one, or the little RO, and then our GM, our conductance. We can solve for all 3 of those here, given what we know. We know beta, we know the early voltage, transconductance, and then we know all the currents. Given that, we can find little RO, GM, and R pi. I'll begin left to right with little RO is early voltage over IC, your current, collector current. This is given on your sheet. Believe this one shouldn't have to be memorized, which in our case would be 100 volts over IC, which is 1 milliamp. You should, I would always on an exam, I would always just use my calculator. Like this is, you can look at this and easily see that's just, this should be 100 kilo ohms. Because we have 100 over 1e negative 3, so it'll be 100 times 1e to the 3. But if you using your calculator, just check it is always helpful to make sure you don't make a simple error. We could check our conductance, GM. Equation is also given to you with IC over VT. That's something I didn't write up here. VT is given. It's not going to change. 26 millivolts. This will usually be the same for most operating temperatures, conditions. We'll see one milliamp. We already know that. And then 26 millivolts. The milli will cancel out. So it's 1 over 26, which is 0.0385. So we'll have 38.5 milliamps per volt. Correct units, we'll see there, GM. And then we'll have our pi, which we know we can solve for, given the still on the equation sheet, shouldn't be something you have to remember, is beta over GM. There's 2 equations for this. Either one would work and should give you roughly the same answer within some rounding. I'd go out to 2-3 digits, but it'll give you, in this case, it gives us like 2, 5, 8, or 9 something thousand. I would round to 2.6 thousand. So we have 2.6K kilo ohms for our pi. All of these are helpful. I would solve most of the time. You can solve for these right away. These are good to have, good to know, because now we can go into the next step, part 2 of solving for these equations. So solving this problem, which is redrawing the circuit. We want to redraw the model to one of those, into one of the models you should be pretty familiar with now after your exam 3 or test 3. So redrawing or drawing out the model here. This one I'll do with you rather than pasting it in. So we'll see here. I'm going to be moving a little bit. We'll start at the emitter end. So on the emitter end, we have that V sig, which is tied to ground. We could still see stuff. So we have our V sig tied to ground. Coming up to that 10 kilo ohm resistor. I'm following here just to show I'm starting where that red is, going up to V sig, up to the 10K. This is where I'm following. And I'll stay in, I'll stay in this area for now. So we go up to our 10K. So we have a 10 kilo ohm resistor here. And then we can branch down. We're still on the emitter side, but we're also going to be able to do something here, which I'll show. So we're on the emitter still. This is tied to ground. There we got that 1 milliamp, and then we have our base. So what we're going to do here is we're going to branch this off, and we're going to say this is where the emitter is. The emitter end is. So looking at that, that would be, let's put it in blue. So let's say blue there, emitter, that'll correspond to right here. So now what we can do is we'll have that little RO, we're going to have that little RO resistance there. And then we're also going to have that 20 kilo ohm resistance here in blue. So I'll leave that in blue there for a second. So in that blue, so we have our pi. Sorry, I believe I just said little RO. That's not little r. That's our pi. That's our pi, my bad. That's what we'll have there. So we'll have our little r pi, which is 2.6K. And then we'll have our base here, which is tied to ground. And that will go to ground. as we just said, with a resistance of 20 kilo ohms. And now we can continue. We can move on. We'll move that out pretty far so we can get a good drawing. Now is where we're going to have our little RO and our GM pi. So we'll draw out, we have our current control, we have our source here. Voltage controlled current source. And then we'll go down and we have our pi, RO, little RO. Sorry, I switched those up. So we have our little RO down here, which is, we said, was 100 kilo ohms. And then we have our GM pi there. Looks good. And then now we can go out to our collector. So going out to our collector, continue, we have a resistance down here. I'm going to draw that. So we have a resistance there where we're looking back up at this. So we're not on the blue anymore. I'm going to do this in red. So the C we'll put there. So the C will be, let's say, here. So going up the C, we have that 8K. And then we go over, we're going to go through this because we're a small signal. And then we'll have 10K. So we have two resistors. And we go out to this. Sorry, that should be out there. So we have those two resistors, that's 8K and 10K. And this is how they'll be drawn. So we have our 8K there. Move out a little bit more, and we'll have our 10K. And these are both connected to ground. They're both going to be connected to ground. And we'll see that because now we're in that small signal point. So we see that VCC there up at the top. So we're connected to ground now because we're in that small signal area. And that's the same reason the capacitors are connected, they're shorts. So if we were in DC, we would lose that. If we were in DC, we would lose all of this and we would lose all of this. But we're in that small signal part. So that's why this is the 8K is tied to ground. So it's the 10K here. And the capacitors are short. So we'll have V out taken out there. So this is what that model would look like. And what it'll look like for us. I'll do this to realize I was off. So that's the model. There's one thing I want to do before we continue with this here is looking at that 8K and 10K. Very circuits one quick thing to notice. Those are easily in parallel. I would combine those and you could just get one load resistor at the end, which could really help you out. Well, not really help you out, but it'll make it look easier on the eye. So 8K, 10K, combine those two parallel. It would be 80 over 18, I believe, because it's just two resistors. So it'd be 4.44 kilo ohms. So I'll actually erase that there. And I'm going to redraw this quickly. Yeah, and then we could just redraw this as 4.4 kilo ohms with our VM. So that's the model. That's what we're going to keep for now. I'm not putting these RPi and the 20K together because I want to split that emitter and that base part, the emitter and base section. These were easy. These ones here were easy to combine because they were both on the collector. This would change some things. It would make it a little harder. Analysis, it's not, I wouldn't, you can't really do that. So cool, now we have the model. Let's start with, rather than the impedances, let's start with the gain. So we're going to do this in 3 steps. We want our gain, we want our input impedance, and our output impedance. I would start with the gain. And to get gain, we know the general expression for gain is your output over your input, V out over V in. That's what we were using for op amps. It's just the regular gain expression we've seen since the start. So I would start with getting a voltage there for V pi. So we're kind of looking on that left side, on that V sig side. And we want a voltage there for V pi because that's going to help us on that GM V pi. And because we want a voltage here on that input and we want a voltage here on that output. And then we'll just one over the other. But they're both dependent on GM V pi. So at V pi, we'll see looking over here, it's going to be a voltage divider with the VE, with the voltage at the emitter. And I'll show you why if you can't already see it. So we have a voltage divider with VE. So continue on from that, we have VE. We'll have that negative VE. And then we have that 2.6K. And then 2.6 plus 20. So we'll have 2.6K over 20K plus 2.6K. As we're writing out more and more, I'm gonna keep the K, but I'm not gonna keep the ohms. Just to be a lot to write. So then we'll see, given that, writing that out, we'll get that should not be VE, that's V pi. It's equal to negative VE times whatever that fraction ends up becoming, which is 0.11. So we could also write that as negative 0.11 times VE. In this case, I'm doing the capital E. It should be lowercase. Actually, I will put it in lowercase. I just don't like doing the lowercase because it's very easy to mistake that E with a C, but it should be lowercase because we're working in the small signal domain. The capital would mean we're in DC. If we had lowercase v with an uppercase E, that's combined. So we'll have that, and then so we got our equation voltage on this side for V pi, and now we want an equation for V out. So at V out, let me copy this so we can see it on this side as we, oh man. So we can see it on this side as we continue. So at V out, we should be little v, little o, little v o. This is at V out, so it's not V out equals. This is at V out. We have, I'm going to solve this when we're in conjunction. We'll be solving for currents because the GM V pi is a conductance. So we have the current law, and we'll have V out over, we'll look at this resistance here. We'll have V out, that to ground. So we'll have here to the 4.4K to ground. So V out over 4.4K kilo ohms, that's a current we have. And another current we're going to have is V out coming down here, over here to VE. So we'll have V out down here over the 100K, over, up, down, and then we'll stop at VE. So that will be from start to finish, we have V out minus V emitter over that 100 kilo ohm. And then we have one last one, which is already there. It's a current. We have the conductance is that GM V pi. And one thing we already, and this equals 0. We already solved for what V pi is. We know what V pi is. So we can plug that into this equation. And that'll help us move along. So we have V out over 4.4K plus V out minus V emitter over 100K plus GM negative 0.11 voltage at the emitter. And that removes V pi. So now we only have V out and VE in the equation, which is helpful. It reduces something else because we know, even though I'm writing GM here, we know what GM is. So we can put in a value for that. We already solved for GM up here. We already solved for GM to be 38.5 milliamps per volt. It's just easier to write GM in the moment. So what I would do here is solve for V out. We want to get an equation for V out, something small. In this case, we're not going to be able to solve for just V out as a value because we have two unknown variables. We don't know what V out is. We don't know what V at the emitter is. But we can get V out equals blank VE, which will be, which is solving it down, moving down. I'll work through the algebra on this. Stop me if you have any questions on it. Sometimes algebra is the hardest thing with this stuff. I begin by, I want to change this. I would split this fraction. So I'd have V out over 100K minus VE over 100K. And then you could keep the GM on the side or move it over. I would move it over. So there we got that. And then we'll see, we can, I'd move the VE over. So now if we move the VE over, then we're keeping V outs on one side and we're moving all the VEs onto the right side. So we'd end up with V out over 4.4K plus V out over 100K equals, then we'll add the VE over, and my bad, sorry, I shouldn't have a minus GMB pi, should be, there we go. So then that would make this positive. And then we'll have VE over 100K plus GM. Actually, I'm wrong. It is plus. I forgot about that negative. We have that negative 0.11 VE. So when we moved this over, we did negative GM times the negative 0.11 VE. So this is actually positive GM and then positive 0.11 voltage at the emitter. There we are. So then we'll have V voltage at the emitter over 100K plus conductance times 0.11 voltage at the emitter. Well, there we are. And now we'll simplify from here. This is now getting to an easier part of algebra. This part shouldn't take too long. I'll pull out a V out on this side. So we'll have 1 over 4.4K plus 1 over 100K. That is a constant. That's going to give us a constant value. And then we could do the same on this side. We could pull out a VE is 1 over 100K plus GM times 0.11, which, remember, GM is 38.5 milliamps per volt. as we had here. So using your calculator, you get V out, and 1 over 4.4K plus 1 over 100K is 0.24 times 10 to the negative 3. And then we have VE, and then we have 1 over 100K plus 38.5 milliamps per volt times 0.11. I just put all that into your calculator. Other than the VE, just do the what's in the brackets here, just that in your calculator. And then we'll get VE equals 4.19 times 10 to the negative 3. And we could solve for V out. So we'll get by dividing, right? We'll divide this over here. So we'll get V out is equal to a value times VE, which ends up being 17.5 times VE. Let me check that, make sure that's right. Should be negative 3. Oh. Yeah, it makes sense because it's divided. So it's over 0.24. Yep, okay. So continuing on from there, we'll now that we have that output V out, we can work on getting that V sig, right? You remember that part is if we have the output, we're on the output part, we need the output over the input, which is going to be on the V sig, to get our gain. That's what we're trying to solve for here. So in that, we want to get that kind of VE side here. We want to get this VE side. We want to solve for the voltage that we have over here. I will once again move to a new page and paste this to keep it going smoothly. There we are. And now we'll do the same thing. So how we kind of wrote out, we had the V out, that current here, and we had the current going out here. We're going to do that, but on the other side now. So we have our voltage at E. It's going to go down over this and then over the 20K as well. So that's 1. And we'll have E over the 10K. There's 2. And then we'll have E that goes, we got that GM V pi. We'll use that again. And then we'll have an E here over the 100K. So we need 4 now. We're not going to have 3. Let's begin, just go straight from left to right. So on the far left, we have the V sig and the E. So we'll be going from E over the 10K down to V sig. So we'll have V at the emitter minus V sig over 10 kilo ohms. Plus, then we have E going down over R pi and then over the 20K down to ground. So we'll have VE minus 0 volts. You don't have to write the 0 volts, but minus 0 volts over 2.6K and 20K. It's series, so they'll just add together. So we'll get 22.6 kilo ohms. And then we have we could do the GMV pi. We'll see that the arrow is going in the opposite direction that we are. So we're going to define that as negative. So we'll have GM times V pi. Remember, we know what V pi is. We're going to change that. So V pi, we don't want it in terms of V pi. We want it in terms of VE. We know that is negative 0.11 times VE. So this will actually become positive GM and then 0.11 VE. And then we have our last current that we have from E here over the 100K over up to the collector. So we'll have our VE minus VC over 100 kilo ohms. And then all this is equal to 0 because now we've gotten all of them. And now we'll do the algebra again. I will do this here on the video in a little less steps. It's the same exact way as we did it with the previous one. The full steps I have written out when I'm going to publish my notes. I have the full steps written out to the algebra if you have any issues going on with it. So we'll have VE. Remember, we want to keep it on one side and one side on the other. Now I'll have V sig on. So we have VE, VC, and V sig in here. I didn't want VC, my bad. I got mixed up. So we have that 100K. It's not VC, it's V out. We're going all the way to V out here. And the reason for that, and you can figure that out, is because we need it in terms of V sig and V out. So we can do that. So we have VE, V sig, and V out. And we'll continue on doing the algebra. We'll have that 1 over 10K plus 1 over 22.6K. So I'm pulling the VE out of all of them. And then we have our GM times 0.11. And then the VE gets pulled out. So GM is 38.5 times 10 to the negative 3 times 0.11. I already did that. My calculator is 4.18 times 10 to the negative 3. And then lastly, we pull out the VE here. We move the V out away, and then we'll end up getting 16.5 over 100K. So this is doing the algebra. It's gonna be a couple steps. And then we'll have V sig over 10 kilo ohms. Because we want V out over V sig here. So, well, and we have VE written in an equation with V out. So if we get VE written in an equation with V sig, then we can use those to get V out over V sig. And we'll see that here as we continue on. So we'll get VE. All of these are constants. So we can just put those all into your calculator, which will give you 4.16 times 10 to the negative 3 is equal to V sig over 10 kilo ohms. And then we could get VE on its own, and we'll use that to plug into the other equations. So we'll get VE is equal to multiplying the 4.16, we have the 10K on the bottom. We'll end up getting V sig over 41.6. You could just do it and get something out into the numerator. The denominator works either way, as long as you have something equivalent. You could have 1 over 41.6, whatever value that is, times V sig. That's the same thing. Using this equation, though, we have an equation for VE here. Well, we have an equation that we wrote on the other page. We're saying V out is equal to 17.5 times VE. Well, we just said that VE is equal to whatever we have here, which is V sig over 41.6. So if we plug it into this, we'll get V out in terms of constants and V sig, which will allow us to get the V out over V sig, which would be our gain. So we have V out is equal to 17.5 times V sig over 41.6. And then we'll have 17.5 over 41.6. And we can divide, so it's 17.5 over 41.6 because we can divide the V sig out. So we'll get V out over V sig is 17.5 over 41.6, which is 0.42, which is our gain. So that's the gain there. And that is part one of the 3 parts that we have to do for this problem. This one is a little long. The next 2 parts of this are easier. So we'll continue on to there. So the first thing we're going to do, let's do input impedance before we do output impedance. We'll have to do both. It doesn't matter which. So when we're doing impedances, what we're going to do is we're going to short the voltage sources and open the current sources except for the voltage controlled or current controlled ones. So that V sig is going to get removed. And then we're going to replace it. We're going to place this whole front part. Looking back at this, we're going to cut off at that capacitor here. We're going to cut off at this capacitor. Like, this doesn't exist anymore in terms of the problem. And then the 1 milliamp is going to be open. So we're going to add a test source here with a current on the input. And we'll do the opposite when we do our output one. So we're going to add our test source to get that impedance there. We're going to add our test source here, which I'm going to name Vx, and then we have Ix. So we have our test source voltage and our current. And that's how we're going to be able to get our input, our in, which is taken here. That's where our in's coming from. So we can use our previous equation where we know that V out is equal to 17.5. And in this case, it's not VE, it's going to be VX. Because we'll see that Vx will be here. That'll be the same thing. They're the same thing in this case. And then we can also use the other equation we already wrote, is we knew V pi was equal to 0.11 VE or negative 0.11 VE. So we could do negative 0.11 Vx again, just like we did for V out. Solving for resistance, we know Ohm's law. Jump back to Ohm's law, V equals IR. We know that R is equal to voltage over current. Making sure, yep. So if we know the voltage and the current at the input, then we know the resistance at the input. So what we need to solve for are what Ix and Vx are. So we want to solve for Ix or Vx. I'll begin with Ix, which is looking at that current. We have the current going here, and we'll go down. So we'll go down this resistor, then the 20K. So we'll start with that one. So we have Ix is equal to, we have our Vx, Vx over 22.6 kilo ohms. And then we have another one, another current that we have going out here. We have Vx going out over the 100K, all the way to V out. And then we have our GM V pi. Those are going to be the other two. So we have Vx minus V out over that 100 kilo ohm resistor. And then we have that GM V pi. We know what V pi is equal to. I just wrote it right here. So we could do negative 0.11 Vx. So we have an equation for our current. And then we have our equation for our current in only terms of the voltages. And we have our Vx and then the V out there. So we can just solve for this, and we could solve for Vx over Ix. So we'll end up doing the algebra. We'll have Vx. We have 1 over 22.6K. Then we'll get the same thing here of negative 16.5 over 100K plus 4.18 times 10 to the negative 3. The following very similar, like these numbers are very similar to what we saw on this page. You'll see here and here.
Isn't GM isn't GM negative? Since we're going
yes.
from the left side?
Yeah, so but sorry, because we have the negative 0.11. So
Oh,
it's
yeah,
negative GM times the negative 0.11. So, and thank you, you did catch me because I did write negative 0.11 here still. So yes, it is negative, you're right. And it's negative GM and then negative 0.11 Vx, which would end up being positive.
All right, gotcha.
Mm-hmm. And then continuing on from there, we have the Ix Vx. We want Vx on the top, so we're actually going to have Vx over Ix equals 1 over this whole thing. How I did that is I multiplied this whole thing over to the left side, and then I divided the Ix over here. So that over that whole thing is 1 over, just doing it already in a calculator, is going to be 4.06 times 10 to the negative 3, which is 246 ohms.
So you don't actually have to solve for anything really. You just do the equation and just flip them so that you already get. Oh, okay.
Yeah, because of the Ohm's law.
Okay. I always thought you had to solve for one of them or both of them, or like actually get a value from them, not just get a fraction. Okay, perfect.
Yeah, because we don't know what Vx is, but we know the ratio of Vx over Ix, and that's the resistance. So, well, and now we know the resistance you could find, but it doesn't matter. That's why we just have a test source.
So that's Rn, right?
This is Rn, yeah, sorry, I'll write that out. R out will follow the same exact thing. We're just gonna, our test source is not gonna be on the input side, it's gonna be on the output side. No, it's gonna look very similar. If I can, I want to move that. There we go. So it's gonna look very similar. We're going to remove the VSIG. It's not gonna be there. It's gonna be tied to ground. That's big. Tied to ground, got the 10K, that 4.4K, and then instead of V out, we're gonna have our test source because we're testing for what the output resistance is. R out. And then we have Ix here. So we'll follow that going in. We'll reuse the same equations. V pi, we know. We can't use V out because V out's no longer there, but we can reuse V pi, as we know is 0.11 times VE. And then I would do those, I'd do the current equations again. So we have our current here going down over the 4.4K, which is going to be Ix, right? So we'll have VC over 4.4K. Then we'll have VC over 100K minus Vx. And then we'll have our GM VE or GM V pi, which is yeah, sorry, GMV pi. So let's write that out. So we'll have V let me look at that. Yeah, so VE minus VX. So that is looking at VE 100K to VX, which is right here. So VE minus VX over 100 kilo ohms. And then we have plus, looking at this, we have three resistors here. The 10K, E to B to the 20K, which all three of those are going to be in parallel. So we're going to have that 10K parallel with the 2.6K and parallel with the 20K. And that'll be our denominator there. So I'll end up having VE over 6.9 kilo ohms. And then we have our GM, V pi, which is GM times negative 0.11. So it's minus GM negative 0.11. VE equals 0. And then again, that would end up being positive. So doing the algebra part of this again, we'll have VE 1 over 6.9 kilo ohms plus 1 over 100 kilo ohms plus that GM and the 0.11. So we'll get 4.18 times 10 to the negative 3 equals Vx over 100K. More algebra, we'll get to VE equals VE times 4.13 or 4.3 times 10 to the negative 3. Lots of algebra with this part. And this stuff was Vx over 100K. As I said, the full algebra stuff will be on my paper that I'll post with this video. I just don't, we shouldn't, spend 40 minutes just on the algebra part. And we'll end up, we want to solve for VE because we know VE, then we can use that to get to our VX, or what we want our VX over IX. So VE, we want to solve for VE. We'll get VE is equal to VX over 430. And now we can go back to our equation for IX, write out our equation for IX, which is going to be VX over 8 kilo ohms. We'll go back up here. We have VX over 8K. And we have minus 4.2 times 10 to the negative 3 over 430 Vx. And we can just solve for Ix is equal to Vx 0.115 times 10 to the negative 3. And then we'll do Vx over Ix is equal to 1 over 0.115 times 10 to the negative 3, which is 8.7 kilo ohms, which is going to be our R out. One part while I was doing that, or this last part here, that I noticed a mistake I made that could definitely give you a question, especially right here on the VX and the 8K. This is not 4.4K anymore. This is 8K. I'll explain why. Is because we removed that V out part, and we're not looking anymore after these capacitors. So this whole part here does not exist in the problem anymore. Where we put our test source here. We put our test source here with the current going up, and then we have R out. So the only resistor we have now is 8K. It's the 8K not in parallel with that 10K. So that 10K isn't there anymore. So that's why I got that. That's why I have that 8K being used here on that VX. So I know it said 6 to 7, but I got another problem, so I'll do it. I'm gonna keep doing it. The next one is question 4, and this one will not take nearly as long as the BJT one that we just did. I need some water because I'm talking a lot. Okay, so question 4. I'm not gonna draw. I already have it drawn, so I'm gonna send it to myself real quick. I don't spend time drawing it either. And then I believe Noah did question 1 and question 5, so I can do and I'm doing question 2 and question 4. So the only one you haven't done is question 3. Or sorry, you haven't done. The only one we haven't done is question 3. So this is what question 4 looks like. And the first thing you'll notice is that MOSFET. For me, the first thing you notice. First thing I notice is a MOSFET. When you see it drawn out, you're gonna have that V sig here, and then that'll be to ground, and then you'll have your 10K that's drawn to ground. I just connected the two because they're both attached to ground there at that point. And then we kind of got the same thing going on with that ID. That's supposed to be here. The ID with that 2 milliamps, we got the same thing going on. So we got a common base or configuration that we see there with that 2 milliamps on the drain source, and then we have our drain. Draw that. My bad, I missed that part. So we'll also get our ID. We know what our ID is, which is 2 milliamps. Our base is tied to ground, which because we know our ID, we can easily find our GM. Because remember the information that was given to us at the beginning here with these questions. I'm pulling up the actual PDF instead of the circuit I drew. For all questions, beta is 100, Kn is 10 milliamps per volt squared. So we know that GM is 2 times Kn ID. So we have 2 Kn ID. We know all of those. So we can find GM, which is going to be the square root of 2 times 10 milliamps per volt squared times ID, which is 2 milliamps. Fix my square root, which gives us a final answer of 6.3 milliamps per volt. And then our R out, little RO, sorry, not R out, it's going to be our little RO. Is VA over ID. VA hasn't changed. Our early voltage hasn't changed. It's still 100 volts over ID, which is 2 milliamps. Those are your quick, easy things we can solve for. So we know that little RO is equal to 50 kilo ohms, the internal. So like we did with the last one, since we found that information, we know that information, we could draw our small signal model going on. Those capacitors will be connected, and then we'll be using a current I sig. And then have this here. 1 second. getting it sent to myself that I drew it earlier when I was working on it. So here's that small signal model we would draw out. We'll see that we have our I sig here. We have our 10 kilo ohm. We have our GM VGS, our RO, our little RO here. We have that 5K up at the top and then our 4K, which we can combine those two again that we saw with the BJT. Those are in parallel. So we can combine those two, a 5K and a 4K parallel. And we know our voltage at the gate based off this. We know our voltage at the gate is 0 volts. So our VGS, since our voltage at the gate is 0 volts, we know that VGS is negative VS. So going to our source, I sig, we have there. We're going to do current law again. So we have I sig. We have a current going here over the 10K down to ground. So we have our V, we'll say our VX here again, or let's do VS. So our voltage source here again over that 10K to ground. So there's one. And then we have our VS here, or volts, well, S here, 10K to ground. And then we have our VS. Let's do it over the RO. So we have VS, and then we have our 50K RO over here to V out. So we have VS minus V out over 50K. And then we have our last one here, which is that GM VGS. And we're going that opposite way again. We have negative GM. But think about it. Remember, VGS is not VGS, it's negative VS. Voltage at the source, because the voltage at the gate is 0. So this actually ends up becoming positive GM VS. And then at the drain, because this was at the source, so at the drain, we can write out what we have too. So we have the drain, we have that 5K and the 4K in parallel, which is 2.2 kilo ohms. So we have here to this, and let's just say this is in parallel. So that over 2.2K. So we have our V out over 2.2K. Then we have our V out to our VS over 50 kilo ohms. And then we are following now the direction of that GMVGS like that to S. So we'll have positive GMVGS, which is actually, I'll write it out just so we don't get confused. It's GM negative VS. So this is actually minus GM VS equals 0. So using that, we can solve for the at the drain. We have V out and VS. We can solve for V out in terms of VS or VS in terms of V out. In this case, we're going to do V out in terms of VS. Go look at V out. And then remember, also a V out over 2.2K plus V out over 50K minus VS over 50K minus GM VS. So we can split everything out. So I'll write that V out over 2.2K plus V out over 50K equals VS over 50K plus GM VS. So we get V out 1 over 2.2K plus 1 over 50K equals VS, and we have 1 over 50K plus GM. And then we'll solve for that, and we'll end up getting V out is equal to 13.3 VS, because we can just divide. We can divide this over here. And we can use that to find our IO, because our IO was dependent on, or I out is dependent on V out. So we can put that back in I sig. So we know our equation for I sig that we wrote out is VS over 10K plus VS minus V out over 50K plus GM VS. So we have VS over 10K plus VS minus V out over 50K plus GM VS. And we can plug that in for V out here. So we'll get VS over 10K plus negative 12.3, sorry. Because we have one VS minus 13.3 VS, which is negative 12.3. VS over 50K plus, we know GM, which we solved to be 6.3 milliamps per volt. So it's 6.3 times 10 to the negative 3 VS. And we could solve. So we get I sig equals VS 1 over 10K minus 12.3 over 50K plus 6.3 times 10 to negative 3. And that looks like an S. 50K. It still looks bad. And then that's a constant there. We have VS times a constant. So that ends up being 162. So, well, it becomes this. We want to solve for VS. So VS equals 1 over this value. 1 over this value times I sig, which is 162 I sig. And 162 is ohms. And then we have V out in terms of that we already solved for is 2.1K times I sig. So I out is equal to V out we get I out is equal to 0.54 times I sig. And we'll see that here. I'll back up for a second. We can look back. So we have V out is 13.3 VS. So we know that VS, if we know that VS is 162 I sig, we can plug that in for V out. So we have 162 times 13.3 I sig. So we get 2.1K I sig. And then we can get I out from there because we have our equation written for I out. So now we'll move on. We'll go to the R in and R out, the last two things. Which
Oh,
these are easier to solve on this one. So we have I'll take this. Actually, I think it's still copied.
I have a question.
Mm-hmm.
So you were trying to get gain on that first step, right?
No, so this question actually asked for something different. So we
Oh.
weren't. Well, yeah, sorry. The gain is, yes, it is correct. Sorry, my bad.
Okay. So you were just doing it based on current, like IO and iSig?
Yeah, because gain is the ratio of output to input.
Mhm.
It doesn't have to be voltage.
Okay, that makes sense. But I guess the thing I'm confused on is like the whole thing you were doing. So, oh, okay, the IO is just divided by the iSig. Okay, is 0.5
Correct.
per gain. Okay. Sorry, I was like, where I didn't see you solve it, but yeah, okay, that makes sense. Yeah, the game. Okay, that makes sense. Okay, never mind. Thank you.
Last thing is R in. Let me put the picture R in and R out. So what we're gonna see here is gonna change a little bit. We got that. We go back to the test source kind of thing. But the test source part of this is gonna look much easier. So we're gonna have our voltage source that we could put here. We're gonna have our current IX. This is our voltage on our source. We'll go out. We'll have our GM-VGS still. And then we'll have our 50K. No output because we'll see where the capacitor was. And we'll have those we'll have the 2.2K here because that's the 5 and the 4 in parallel. And then we'll just solve for Rn, which is easier, much easier than what we had with the BJT. We know resistance is voltage over input, input voltage over current. Ix we have here, I'll rewrite this. This should be a little I, little v. We'll have Ix is equal to, we'll look back at it. We'll have Ix, so we'll have that Vx going up and then over the 50 kilo ohm RO out. And we know what Vs is. We know that Vs V out is equal to 13.3 Vs, but it's not Vs anymore. It's going to be Vx. So here we had Ix is equal to Vx minus V out, as we have Vx over 50K over out to V out. Well, V out is actually 13.3 Vx over 50K. And then we have our GM-VGS, which we're going backwards. So it's minus GM-VGS is still negative Vs though. So it'll be positive. So we'll have Ix is equal to Vx, or actually it's going to be negative 12.3 Vx over 50K plus GM-VS. Which is not Vs, it will be Vx because of our test source. We'll see that there, that the voltage that we have here is the same. The voltage at this point is the same at this point. So Ix is equal to Vx negative 12.3 over 50K plus GM. And we know what GM is, and so this is a constant. So we get Vx over Ix for our input is 1 over negative 12.3 over 50K plus GM, which is roughly 165 ohms. Our out's going to be the same thing, but the test source is going to be on the output, not the input. So we'll have our 10K on the input. We'll go out, we'll have our, I'm going to move this down so I have more room. Our, this, we'll go up, we'll have our 50K RO. Keep going over, and then we'll come down to our 5K. And
Sorry, I have a quick question. So when we're doing the RN and R out like circuits, like for the R, you kept the 5K and the RN circuit, but you like it's supposed to be taken out, right?
yeah,
Leave it in
so
because it doesn't like you're not well, it's just easier on the eyes because you won't touch it at all. Basically, if you
yeah.
don't add it. Okay, that makes sense. I was just making sure because you added the 10K on the R out, and I just wanted to make sure that yeah, okay, that makes sense. Okay, perfect.
Mhm. Yep. Oh, um, yeah, looking at the original circuit. Oh, it helps if we look at the original circuit for this. Yeah, exactly. Exactly what you said. Okay. Cool. So yeah, continuing on from there, then we do the same thing. We'll have our VS. So we'll start over here. We'll say this is VS. So we are VS over the 10K. Plus, well, our VS here over the 50 down to the test. So a VS minus VX over 50K. And then we have that GMVS equals 0. And remember that was negative GM, negative VS. So it's positive GMVS. And then we'll solve for VS in terms of VX. So we'll get VS using skipping some algebra parts again. We'll have 1 over 10K plus 1 over 50K. It's the same idea as what we've been doing previously, splitting up that middle fraction and then separating VX and VS. So we'll get VX over 50K here. And then to get VS alone, we divide that whole everything in the brackets, which will end up giving us VX over 321. And now we can go to the test source. So the test source at VX, and then we'll solve for, we can put it in terms of IX. So IX there will follow that. So IX is equal to this VX over down to ground. So we have VX to ground over that 5K. Then we have the VX over the 50K there to VS. And then we have our positive GM VGS, which ends up becoming negative GM VS is equal to IX. And then we know what VS is in terms of VX. So we have IX is equal to VX over 5 kilo ohms plus VX minus VX over 321 over 50 kilo ohms minus GM VX over 321. And then we solve algebra stuff for that. We end up getting IX equals VX 0.2 times 10 to the negative 3. It's what all these values end up coming out to. GM, remember, is a value that we already know, which means that VX over IX, in this case, is our output resistance is 1 over 0.2 times 10 to the negative 3, which is 0.2 times 10 to the 3, which is 5 kilo ohms. Sorry. 1 over 2 times 10 to the 3. So 1/2 times 0.2. 1 over 0.2 is 5. And then it's 5 times 10 to the 3. So correct. I would still recommend putting that in your calculator, not doing it in your head. So I know that last part, bit rushed, but it was the same idea. It was the same thing, same algebra. I just kind of skipped through a couple parts because it was the 4th time we'd done it. But I do have the full notes to that in the notes that I'm going to post for you to use. This notebook was really just me going through it together, looking at this is what I have, and I write out everything for you to fully understand, walking through all the algebra and everything, which is step by step. That's what I'm going to post for everyone. So that's all. If you have any questions, you can email me. I'll be available. I know your exam is on Thursday, so it gives you tonight and then Tuesday, Wednesday. And I will not be having a problem session on Thursday because of doing this today, which I thought was better than doing it after your exam 4, which is your last exam before your makeup. If you're doing that. So great. Thank you again. Any questions? Feel free to ask.
Yeah, I just have a question about like doing the circuits.
Mm-hmm.
Like at the beginning, when you're trying to get all the equations for VO and VSIG,
Mm-hmm.
I'm a bit confused because I know what the like is the one where the resistance is parallel to the current source. Is that just for like specific? Because I'm looking at the what is it, the cheat sheet that we're gonna get, and doesn't match in a sense.
Yeah, no, so it won't
Or
always
like it's
be.
in a different area or a different way they're putting it. I'm just kind of confused on it.
Mm.
So is it only for common drain circuits?
Base.
Or
Yeah, common base.
common base. Okay, okay. And you know it's a common base by
Because the base here on the left side is tied to ground with nothing, no source.
nothing. Okay, okay. Oh, and then common drain is when drain is connected to ground, nothing else.
Mm-hmm.
Okay, okay. Okay. That makes sense.
Yeah, looks good.
Yeah. Probably had to do a little bit more problems on it, but just to get familiar with it. But yeah. That was my only question. I was kind of yeah.
Yeah, no worries.
Um
No, here, I'm gonna stop the recording. In a second.